Imagine a future where AI doesn't just, understand language or generate these incredible images, but can actually do both seamlessly. Like think creatively, express itself across different modes. Almost like us.
Yeah, it sounds like sci-fi, but it's really where the cutting edge of research is heading.
Exactly. Welcome to AI Peer Review, the show where we dive deep into the latest research papers and pull out the key insights for you. Today, we're tackling a really fundamental challenge in AI. How do we get these powerful large language models, the LLMs, with their amazing reasoning skills, to work smoothly with diffusion models that create super high-fidelity images?
And the key question is, how do you do that without messing up either model's strengths? It's a tricky balancing act.
It really is.
Yeah.
And we've got an interesting paper here that might just offer a breakthrough. Bifrost-1, bridging multimodal LLMs and diffusion models with patch-level CLIP latents. So our mission today is to unpack Bifrost-1. It promises high-fidelity, controllable image generation, yes, but also much better training efficiency. And crucially, it claims to preserve the core reasoning abilities of the multimodal LLMs, or MLLMs.
Right. Which is often the part that gets compromised.
So what does this Bifrost-1 approach really mean for the future of, well, unified AI?
It's a great question. And to understand Bifrost-1, we first need to look at the landscape, how people have tried to do this integration before. The paper lays out two main paths.
Okay, let's unpack those. The paper mentions these two paradigms.
Right.
And their limitations. Can you walk us through them? Why haven't they quite cracked it yet?
Sure. So the first way, figure 1A in the paper, they call single architecture approaches. Basically, you take an LLM or an MLM and you fine-tune it to generate images directly. Think models like Chameleon or EMU3.
Okay, so one model does it all.
Kind of. The appeal is that unified reasoning and image creation. But the big downside is the cost. Getting really good images takes a ton of computation.
Oh, the expense factor.
Exactly. And there's another risk, a pretty significant one. If you're not super careful with how you train it, you can actually hurt the LLM's original language skills.
Oh, wow. So you make it good at pictures, but maybe not so good at reasoning anymore.
Precisely. It's like teaching a brilliant writer to paint, but they sort of forget how to write compelling stories in the process. You undermine the whole point.
Is that something people are fixing, or is it just inherent to that single model approach?
Well, people are definitely working on it, but it's tough. Fundamentally, you're asking the same set of parameters to juggle very different complex tasks, intricate language, and pixel-level generation. It often leads to a compromise somewhere. It's a capacity thing. Okay, so the second approach, figure 1B, is what they call bridging-based approaches with 1D tokens. Here you have your LLM or MLLM generate, say, a text description, or maybe these continuous 1D query tokens.
1D tokens, like a simplified code.
Sort of, yeah. And these tokens then guide a separate pre-trained diffusion model. You see this in methods like MetaQuery or DreamLLM. They're generally more efficient to train than the single architecture ones.
Okay, sounds better, but limitations.
Definitely. Text descriptions alone can be too, sparse. They often miss the fine-grained details. Imagine trying to describe a complex painting perfectly with just words. You'll miss stuff.
Right. Nuance gets lost.
And with those 1D query tokens, even though they're continuous, learning good ones often needs a big connector module and lots of end-to-end training. Plus, they still struggle to convey really detailed 2D spatial information.
Like where things are positioned in the image.
Exactly. Where objects are, how they relate spatially. That's hard to capture well with just a 1D sequence.
So it feels like we're stuck. Either it's super expensive and risky for the LLM's brain, or it's more efficient, but you lose detail and spatial control. Like building a bridge that doesn't quite reach the other side.
That's a good analogy. And this is exactly where Bifrost-1 comes in, aiming to be that sturdy, efficient bridge.
All right, so how does Bifrost-1 build this better bridge? Figure 1C shows their approach, right?
It does. The core idea, the real innovation, is how it connects the pre-trained MLLM and the diffusion model. Instead of text or those abstract 1D tokens, Bifrost-1 uses 2D patch-level CLIP latents.
Okay, 2D patch-level CLIP latents. That sounds specific. Why is that the key?
It's absolutely key because these latents are, you could say, natively understood by the MLLM's own visual encoders, the CLIP part of it.
Natively understood.
Yeah, think of CLIP latents as a sort of universal fingerprint for an image or part of an image that the MLLM already knows how to interpret. This alignment is crucial. It's like finding a shared language.
So no need for a complex translation step.
Exactly. The MLLM can generate rich, spatially precise guidance for the diffusion model without having to learn a whole new visual language or undergo costly realignment. This makes training way faster and more efficient. It's a really clever use of existing alignment.
Okay, that makes a lot of sense for efficiency. So Bifrost-1 has two main goals then.
Right. Goal 1, keep the MLLM's understanding capabilities fully intact. Goal 2, efficiently teach the MLLM to generate these specific CLIP latent tokens to guide the diffusion model effectively.
Find the common ground, leverage it for efficiency, and keep the original smarts. Okay,
Yeah.
I'm following. So how do they actually build this architecturally? Let's maybe get into the technical weeds a bit, looking at Figure 2.
Absolutely. Figure 2 lays out the Bifrost-1 architecture. It really boils down to two main components, and they're both designed quite cleverly. First, you've got the visual generation branch. This is actually built into the MLLM itself.
Okay, part of the MLLM.
Yes, and here's the ingenious part. How it's initialized. They don't build it from scratch. They initialize its parameters, the attention projections, QKV, the MLP layers, the normalization layers directly from the original MLLM.
Wow, so reusing existing
And
parts.
heavily reusing. The only really new piece is a simple linear layer that acts as the vision head. This massive parameter reuse is vital. It avoids that whole costly, complex process of realigning image embeddings you see elsewhere.
Right, the expensive part we talked about.
Exactly. And critically, it helps preserve the MLLM backbone's original reasoning power. This is how they avoid that forgetting problem.
So they're not just adding a skill, they're repurposing the MLLM's existing visual understanding pathways. That sounds really efficient.
It is, and the way they train this branch is using something called masked autoregression, or MAR.
MAR, how does that work?
During training, they take the input image embeddings and randomly replace parts of them with a special mask token, M. Then, the MLLM's job is to predict the original embeddings for those masked parts, essentially, filling in the blanks.
Okay, like a closed test for images.
Sort of, yeah. Then, during inference, when you want to generate an image, it starts with all masked tokens and iteratively denoises them, predicting the CLIP embeddings step by step until it forms the complete representation, like refining a sketch.
Interesting. And the second component, you mentioned a latent control net, top right of Figure 2.
Right, the latent control net. Now, ControlNet itself isn't new. It's a popular technique to guide diffusion models. But here, it's a lightweight adaptation. Its job is to take those patch-level CLIP latents generated by the MLLM's visual branch and use them to guide the main diffusion model, like FLU X.1 dev in their experiments.
Lightweight how? What did they change?
Two key things. First, they replaced the input linear projection layer in the control net to make sure the embedding dimensions matched up correctly between the MLM's output and what the control net expected. Simple, but necessary.
Okay, alignment again?
Exactly. Second, they added a lightweight 2D downsampling convolution block. This reduces the resolution of the visual embeddings by half before feeding them into the control net.
Why do that?
It makes the guidance process even more efficient, computationally cheaper, while still keeping the essential spatial information the control net needs. Smart optimization.
And training this control net. Is that expensive or is it lean too?
That's another big win for efficiency. It's incredibly lean. They only update a tiny fraction of the control net's parameters during training.
How tiny? Okay, think of DIT blocks as core processing units in these models. Bifrost-1 only fine-tunes, like 4 DIT blocks and one single DIT plec in the control net. Compare that to the full FLUX.1 dev model, which has 19 DIT and 38 single DIT blocks. It's a massive difference.
Wow. So most of the diffusion model stays frozen.
Pretty much. This decoupled training means they can focus compute on the MLM's vision branch, which boosts performance, and it drastically cuts down memory needs compared to training everything end-to-end. Very efficient.
Okay, the whole approach sounds incredibly resourceful, leveraging existing alignments, reusing parameters, lightweight components. But, the proof is in the pudding. Does it actually work better? How did it stack up in the experiments?
That's where it gets really convincing. The paper provides some strong evidence through ablation studies and comparisons. Table 1 is particularly interesting. It digs into the design choices.
What's the main takeaway from Table 1? Does the choice of latent really matter that much? Oh, absolutely. It shows a clear, quantifiable benefit to using those patch-level CLIP latents.
Yeah.
If you try alternatives like 2D learnable query tokens where the model learns from scratch.
Without that native alignment.
Right. Performance tanks, FID, SFID go up, IS goes down, all indicating worse image quality and diversity. It shows that learning those representations from scratch needs way, way more compute.
Okay. What about other latents?
Same story, VAE latents, which aren't natively aligned with MLLMs, slower learning, worse results. Even using a different, non-aligned external encoder like SIGLIP, still significantly worse than using the MLLM's own CLIP encoder. It just hammers home how vital that native alignment is for efficiency.
So that universal translator idea really holds up in practice.
Definitely. And Table 1 also compares their latent control net guidance mechanism against using cross-attention. The results show that directly injecting the 2D tokens via latent control net gives better image quality. It seems to be more effective at enforcing the spatial structure, telling the diffusion model where to put things more precisely.
Okay, so the specific latent and the integration method are both critical. Makes sense. But beyond efficiency metrics, how good is it at just, well, reconstructing an image? And how does it compare to other big models?
Good question. On image reconstruction, they looked at metrics like RFID, SIM, PSNR, LPIPS, basically measures of how close the generated image is to the original.
Higher SIMPSNR, lower RFID LPPS is better.
Correct. And Figure 4 shows that reconstruction quality improves nicely as you use more patch-level CLIP tokens, like using 256 tokens gets better results faster than using fewer, even with minimal training. The examples in Figure 5 really show this visually. More tokens means more detail, better textures, sharper shapes.
And compared to others, like GPT-4o.
Yeah, Figure 6 shows that Bifrost-1's latent control net achieves competitive, sometimes even better, reconstruction quality compared to strong bit lines like GPT-4o and MetaQuery.
That's impressive, especially if it's trained more efficiently.
Exactly. They achieved this even with much less compute, which is a huge point in its favor.
Okay, efficiency win, reconstruction win. But what about that critical point preserving the MLLM's brain? Does Bifrost-1 avoid degrading the original reasoning skills?
This is probably the most important outcome, and yes, it nails it. Table 2 shows that Bifrost-1 fully inherits the visual understanding capabilities of its base MLLM, like Qwen 2.5 VL7B in their tests.
Oh.
Because the original MLLM parameters are kept completely frozen during the vision branch training. No updates. So unlike methods that fine-tune the whole backbone and risk that catastrophic forgetting...
Where it forgets its original skills.
Right. Bifrost-1 avoids that entirely. The new image generation skill is purely additive. It doesn't come at the cost of its reasoning abilities.
It's huge. It's not a zero-sum game then. It's truly expanding the model's skill set. Okay, final piece. The actual generated images. Are they good? Does the efficiency compromise visual quality compared to state-of-the-art?
No major compromise there either. Table 3 and Figure 7 show it achieves competitive visual generation quality. It holds its own on benchmarks like COSIO and MJHQ for general quality, and also on prompt following tests like Genevol and DPG Bench.
Competitive even with less training data.
That's the kicker. It achieves these results even when trained on significantly fewer image-text pairs. We're talking maybe 9 million or 62 million images versus competitors using 100 million, 200 million, or more.
Wow.
Now, they do acknowledge that raw FID scores can sometimes be influenced by the specific diffusion backbone used, like FLUX.1 dev had some aesthetic tuning. But overall, getting such strong results with that much less data speaks volumes about the efficiency and effectiveness of the Bifrost-1 bridging approach. It means faster development, potentially lower costs.
Incredible efficiency. Okay, last technical point, inference time. How fast can it actually generate an image? Does tweaking the MLLM decoding steps create a bottleneck?
Table 4 addresses this. Yes, more MLLM decoding steps generally give better quality latent representations, but take a bit longer. However, and this is key for you, the MLLM decoding part is not the main bottleneck.
Oh.
What is the diffusion model itself? For example, 8 decoding steps in the MLM might take, say, 0.66 seconds. But running the FLUX.1 dev diffusion model, even guided by the efficient latent control net, takes around 14-15 seconds.
I see.
So the MLM part is relatively quick. This gives you flexibility. You can choose fewer steps for faster generation if you're iterating, or more steps for potentially higher quality final images, and the MLM time won't be the dominant factor holding you back.
That's really practical. Okay, let's pull this all together. What does Bifrost-1 really mean for you, our listeners, interested in where AI is going?
Well, I think it represents a really solid step towards truly unified AI systems. You get high fidelity, controllable image generation, which is great, but you get it with significant training efficiency gains, largely thanks to that clever use of patch level CLIP latents that the MLLM already
And
understands.
critically,
And critically, you preserve the MLLM's original reasoning and understanding capabilities because its core parameters stay frozen. It's not trading one skill for another, it's adding a new dimension. It feels less like a hacky bridge and more like a properly integrated system.
It really does point towards AI that can genuinely think and create across different modalities, more like humans do, but perhaps more efficiently built.
Exactly. And while Bifrost-1 shows impressive results already, especially given the reduced computational resources used, the paper suggests there's even more potential. Scaling this up with larger data sets, maybe even more powerful MLLM backbones.
Right, which leads to a fascinating final thought. If we can get this kind of efficiency and unified capability now, how much further can we push these boundaries? What happens when building these powerful multimodal AI systems becomes even more accessible, less resource intensive? What kinds of truly new applications might pop up when more researchers and developers can actually build and experiment with them? We could be on the verge of some really interesting developments.
It definitely opens up possibilities.
indeed. Well, that's our deep dive into Bifrost-1 for this session of AI peer review. We hope you found these insights into the future of multimodal AI valuable. Thanks for tuning in.